All right. So this is, if I'm being honest, this is probably going to be one of the most important videos that you'll be watching in this course. This is one of the most, if I were to sit here and say, like, if you only had like 15 or 20 minutes to watch a single video, this is probably it. Right. So obviously, in the kind of intro to MCAT math section, we've already talked about dimensional analysis. We haven't really talked about stoichiometry much, but I'll explain what that is here. Um, in Gen Chem, dimensional analysis is pretty predictable, and it's one of the higher yield math abilities that you're going to need. So I've kind of alluded to it. I alluded to it in the intro section, and I also alluded it into the most recent video with the just intro to Gen Chem basic stuff. I actually have a little bit of like a flow chart or diagram, if you can call it, that if you can just memorize it, it's going to walk you through exactly how you're supposed to be doing a dimensional analysis. So this isn't a fix for whenever we're doing something with dimensional analysis, maybe in biology or physics, or just something that's not one of these units that you're about to see. But so that's why, like, I still recommend being able to have the ability to cancel out units willy-nilly whenever you can to be left with something else. That's what dimensional analysis is. This is something that if you just memorize this, basically what the flowchart that I'm about to draw, like I said, it's going to kind of walk you through everything. So basically, the first thing that we're going to do is we're going to talk about the combustion of ethane. So the equation for ethane is C2H6. That is that's supposed to be a 6. C2H6. That is the equation for ethane. And the generic formula for combustion reactions, I believe ethane is a gas, but that's not going to matter for what we're doing right now. The generic formula for combustion is that we take some sort of organic fuel, we add it to oxygen gas and heat. We don't need to worry about that. And that's going to form carbon dioxide gas and some water. Could be water vapor. Could be liquid water, probably a mix of both. I don't really know, if I'm being honest. But this is the basis of how campfires, well, most fires essentially happen. This is how you're providing heat if you have a gas stove, this is what you're doing. This is if you live in a state that still derives all of its energy resources from fossil fuels, this is what is happening to provide energy. We are combusting some sort of carbon source, which provides energy. Obviously, that's not really drawn in here, but produces carbon dioxide. So this is a generic formula that you probably do need to know for the MCAT. But I'm just going to write this out really quickly, and we need to balance it. It is not balanced. So my recommendation for how to balance combustion reactions, this is pretty much one of the only times I'm going to talk about balancing, because that's outside of redox reactions. It's kind of just as long as you can just multiply numbers together to get numbers that make sense, you're going to be fine. That's not like a crazy skill that you need to practice, maybe like you did in your Gen Chem class. But typically for combustion reactions, I recommend starting with carbons. So we're going to even out the number of carbons on this right side. So now we have 2 carbons, and now we're going to do the hydrogens on the right side. So we have 6 hydrogens on the left. That means we need 3 of these hydrogens on the right. And then from there, the oxygen, we'll need to basically throw a number right here just to make the number of oxygens balance what's on the right. So we have 4 oxygens right here and 3 right here. So technically, this should be 3.5. But that's not possible, so we're going to have to multiply everything by 2. Right? I think I did that math correctly. Yeah, I did. We're going to have to multiply everything by 2, so this is going to become a 6. This is going to become a 4. This will become a 7. I'm going to add my little line through it. And then this right here is going to become a 2. Right, I think I've balanced this correctly. Just bear with me if I haven't. Sorry, I'm tired, but obviously I want to make sure that I have it. So I'll check it really quickly. We have 4 carbons, 12 hydrogens, and 14 oxygens. 8 plus 6. Yeah, okay, it's balanced. Okay, so basically, we're going to be using this reaction to basically talk about something. So I'm going to give you an example problem. Right, what they could ask you is if we started off with 0.5 moles, start with 0.5 moles of, I'm not even going to do moles. We're going to do, no, we'll start off with moles. This is fine. If we started off with 0.5 moles of ethane, they could ask the question, how many moles of carbon dioxide would we make? Let me put this in green. How many moles of carbon dioxide would we make? This is the product that we're looking for. Right. So just to kind of make this easier, I'm going to go ahead and draw the figure and kind of explain what each part of it means, right? So in this figure, whenever we're going from left to right, that is going to be our dimensional analysis. And whenever we're going up and down, that is going to be our stoichiometry. That's going to make sense here in a second. So the way that I typically word this is you can only do dimensional analysis within one language. So pretend that the ethane can only speak Spanish. So we can only do dimensional analysis in Spanish with values that explain ethane. And then in order to understand something about this carbon dioxide, we're going to have to convert that Spanish into whatever carbon dioxide speaks. I don't know, French. Carbon, sure, we'll go with that. We're trying to convert Spanish to French, right? So Spanish, whenever we're going from one thing in Spanish to the other, that is dimensional analysis. Basically, if we're just converting moles to density to concentration or something of ethane, that's only describing the ethane. If we need to convert it to carbon dioxide, that's where we're going to have to do stoichiometry. So let me just write everything out here. So we're going to start off with density. So through dimensional analysis, we can convert density to the number of grams, mass, I guess I should say, the mass by multiplying the density by the volume. That's going to cancel out liters and leave us with mass. We can then convert mass into the number of moles by dividing the mass by the molar mass. And then finally, we can convert the number of moles to a concentration by dividing the number of moles by volume to get to concentration. Right? This is dimensional analysis, but I've just written out the pathway for you. We can also just go the opposite direction and then just write the opposite sign under, like, I'm going to go ahead and draw all these arrows and then I'll come back and write it. Sorry, there is an arrow tool. I'm using Zoom to draw this, so I should realistically be using that. Sorry. But basically, we can go back and just do the opposite. So if we're trying to go from mass to density, then we're going to be dividing by volume, right? Which makes sense. Density is equal to mass divided by volume. If we're trying to go from moles to mass, then we're going to be multiplying the number of moles by the molar mass. That's going to cancel out the moles and leave us with mass. If we're trying to go from concentration to moles, then we're going to be multiplying by the volume, which should make sense. Concentration, I'll write the units underneath. Concentration is moles per liter. Moles is obviously just in moles. Mass is in grams, and density is in grams per liter. Right. So notice that in order to cancel out the liters, we have to multiply volume. Then once we get grams, in order to cancel out the grams, we would have to have moles somewhere. That's what the molar mass does. We'd be divided by molar mass in that example. So this is doing all the work for you, essentially. So notice that I gave you moles and we're looking for moles, so we don't really have to do anything with dimensional analysis in this question. We will in a second, spoiler. That is dimensional analysis, right? So if I were to have given you like density of ethane or something like that, you could go left and right as long as I gave you the proper values. Like if I gave you volume and molar mass, you could go from density all the way to concentration if you wanted to, but that is only describing the density, concentration, or mass of ethane. If we need to convert that to moles of carbon dioxide or some sort of property of carbon dioxide, this is where stoichiometry is going to come in. Stoichiometry. And I'm just gonna say like species conversion, I guess is what I'll say. So in this example, essentially, if I want to get from moles of ethane to moles of carbon dioxide, I'm going to have to compare their molar ratios, their stoichiometric ratios. So in this, notice that for every 2 moles of ethane, we produce 4 moles of carbon dioxide. I can basically write this like a cross multiplication. So if you have 2 moles of ethane, this is like the theoretical if you have 2 moles of ethane, oh my gosh, 2 moles of ethane, that is going to react theoretically to produce 4 moles of carbon dioxide. But in reality, we were given 0.5 moles of ethane. So now we're just solving for an X number of moles of CO2. If you're quick-witted, you'll basically get that it's 1 mole of CO2. You can do the cross multiplication if you want, but that's all you have to do, essentially. To do the stoichiometry check, you just have to look at what you're given to what you're trying to get to, create a ratio with the expected ratio of moles with what they actually gave you to solve for whatever variable that you're looking for. Then now we are in moles of CO2. At this point, we now have 1 mole of CO2, so maybe like if they give us the volume, we could have gone and solved for concentration or something like that. That's something I'm going to save for some of the guided, I think I'm going to do a guided practice video for this. Yeah, probably just one really quickly. But this is basically how you're supposed to be doing, this is how I recommend doing dimensional analysis in stoichiometry. I think using this figure will make your life quite a bit easier. But just really quickly to show you an example of how you can actually do this pretty quickly. Let's just say that you start off with a 2-liter concentration of a 2-liter solution that has a concentration of math. We'll say 2 moles. Why not? Pretty strong concentration. And I am looking for how many grams of carbon dioxide are produced. Right? Okay. So, like I said, since we were given the red language, I think I said it was Spanish, stuff about ethane, I gave you concentration and volume. And notice that in order to get to green, I have to go through this stoichiometric species conversion. So I have to get the moles first. Basically, in chemistry, we do not care about how many grams or the concentration or the density of something. We care about how many moles they are. Chemistry happens on a molar basis, like things react due to how many moles that they have, not how many grams that they have. So basically, what we need to do first is we need to take this volume and concentration and convert it to moles. So if we have a 2 molar concentration, X number of moles over 2 liters, that is going to give us 4 moles of ethane. So this is how much we actually have. So now we need to go through and do the stoichiometry check. So if we have 4 moles of ethane, I'll write that we're doing this now, stoich. We just did dimensional analysis. I'll do dA. We did dimensional analysis to convert the ethane to moles. Now we're going to be doing stoichiometry to convert 4 moles of ethane. The typical ratio is 2 to 4. Let me write that first. We have the theoretical on the left and the actual on the right. So the theoretical is 2, this 2 right here, to 4. What we are actually given is 4 moles of ethane, and we're trying to solve for how many moles of carbon dioxide that's going to produce. And that is going to be equal to 8 moles of CO2 produced. Right, so now we can take this number and send it through dimensional analysis, right? Because now we are here. We are now at moles. We have the number of moles in the green language now, so now we can go left and right with the number of moles of carbon dioxide, right? We went through our language conversion. We now have the number of moles of carbon dioxide, not the number of moles of ethane. So now we are here, and we just need to get to grams. So notice that we just need to go to the left. They will give you a periodic table on the exam. The molar mass of carbon dioxide is about 44 grams per mole, if I'm remembering correctly. So molar mass is equal to 44 grams per mole. So notice that if we're going from moles to mass, all we have to do is just 8 moles of CO2 times the molar mass of CO2, which is 44 grams in every mole. The moles will cancel out, and we are left with 8 times 44. That's 8 times 40 is roughly 320. That's good enough for me. 300, I'm going to estimate this, basically 320-ish grams of carbon dioxide produced. Right? Long story short, whenever you're given a property, you can move left and right with that property. Species. If I give you ethane, if I give you some sort of value about ethane, you can move left and right with that property of ethane. If you're trying to figure out the property of something else, you have to go through this stoichiometry check. You have to convert you have to convert yourself from the red language to the green language. You have to go through this stoichiometric ratio thing that's like, oh, typically they react at a 2-to-4 ratio. We were actually given 4, so that's going to be 4-to-8. 8 moles of carbon dioxide. Now you're in moles of carbon dioxide, and now you can get to whatever you need from there. Right, so this is going to make a little bit more sense whenever we do some guided practice. We'll probably do like 2 quick questions on that because I think this is going to catch on pretty quickly once you have this figured down. But yeah, we'll leave it at that. Obviously, this is a pretty lengthy description of dimensional analysis and stoichiometry, but like I said, I think it's one of the more important things to be able to do on the MCAT. I would highly recommend that if you're only going to watch one video, if this is the only thing that you're going to do in this course, I recommend it to be this, essentially. Very important skill, highly recommend it, and like I said, hopefully this is going to make your life a lot easier. All right, that's it for this one. I will see you guys in the guided practice.